remember what do we mean by automatic protection? I explained it. What do we mean by automatic protection? Oh, maybe you have forgotten. The concept was that if you have a three-phase induction generator which is not connected to the grid, and you have here capacitor banks, you have here the capacitor banks, can be connected, of course, in star or in delta. Then let me try here. Then if you have a short circuit here, what happens? The capacitors will not generate any reactive power. Then what happens? There will be no voltage buildup, and then this current will not be too high.
Dr. Hashemia, your screen is not visible to us.
Oh.
Sir, it is visible.
Let me check the problem.
Sachin, is it visible?
Yes, sir.
What's the problem?
Sir, yes, sir, I've sorted it out. It was at my end, sir.
What? The problem was from my side or not?
No,
I don't
sir.
know.
It was from my end, sir. Now it is visible.
Oh, okay, no problem. So my question was, what is the meaning of automatic protection? Automatic protection means that if there is a three-phase short circuit at the terminals of a self-excited induction generator, then the short circuit current will not be too high, of course, at the steady state. The reason is that if you short circuit the terminals, then you have also short circuited the capacitors across the stator of the self-excited induction generator. When the capacitors are shorted, then the voltage across each capacitor is zero. Then the reactive power generated by the capacitor supplied to the machine will be zero. And when the reactive power is zero, then the magnetic field in the air gap of the self-excited induction generator will diminish and will reduce almost to zero, other than the remnant magnetism. When you don't have the flux, then you will not have voltage, and when you will not have voltage, the current will not be too high. I hope that you have got the issue. This is one interesting characteristic of this kind of generators. Did you get my idea?
Yes, sir.
Oh, thank you. And of course, there are several disadvantages of the induction generators. They need reactive power, and also they have poor voltage regulation. Large change of terminal voltage with load is a problem here, mainly for loads which are very sensitive to voltage variations. And this problem is more severe for inductive loads. So we have a very poor voltage regulation, especially for inductive loads. Also, due to saturation of the core of the machine, it is inevitable. We should have saturation to have voltage build up, but this saturation leads to high harmonic content of voltage. And in case of a machine which is connected to the grid, injection of harmonics to the grids, in case, of course, we use power electronic devices. The first one is the case for self-excited induction generator, which the core is saturated. And the second one, which we have injection of harmonics, which are known as switching harmonics, is for the grid-connected induction generator with power electronic device interfaces. So in both cases, we can have the problem of harmonics. Of course, the source of harmonics is totally different. For the self-excited induction generator, the source of harmonics is saturation. It is magnetic. But for the second type, which are grid-connected, the source of harmonics is switching harmonics. This is related to power electronics. Then I explained the phenomena of voltage buildup in a self-excited induction generator. You have a volt-ampere characteristic like the one in the left-hand side. This is related to the magnetization of the core. So this is for the core, and the right side is volt-ampere relation for the capacitor. And you have to find the point which the two curves intersect each other. Of course, at no load. At no load, you have a volt-ampere characteristic from the core, which is related to the V and H curve, and you have also a volt-ampere characteristic for the capacitor. The slope is equal to reactance of the capacitor. And if you intersect, then you can find the operating point. For example, for a value of the capacitor, you will be here. And if you reduce the capacitance, then you have increased the reactance, and then the slope is getting higher and higher. And you see that if you increase it further, then the voltage will drop suddenly. You will almost have no voltage, just a few volts due to remnant magnetism. So this is the phenomena of voltage buildup in self-excited induction generators. Of course, we can explain it step by step, assuming that firstly we have a small voltage. Then this small voltage will cause a current in the capacitor. This current in the capacitor will lead to increase of the voltage. We will come here. Then from this voltage we can come here and then continue. This phenomena is known in control theory as positive feedback. And what does not let that the voltage go to infinity is saturation. So this is another explanation for the voltage buildup. This is positive feedback between the flux and the voltage. If you have more flux, you will have more voltage. If you have more voltage, then this voltage is also across the capacitor. So the capacitor will have more current. If the capacitor has more current, then the reactive power generation of the capacitance will be higher. If the reactive power of the capacitance is higher, then you will have more flux. Why? Because you know in your electric machinery course that a capacitive load connected to a machine, to an AC machine, has magnetizing effect on the air gap flux of that machine. Which this phenomenon is similar to what we have in synchronous machines. If a synchronous generator is connected to a capacitive load, then the armature reaction will have magnetizing effect. This is exactly something similar to that case. And then we have a comparison of self-excited induction generator and self-excited DC generator. So let us go further. We have discussed this. Then we came to the equivalent circuit of a self-excited induction generator. This equivalent circuit is something similar to that for the conventional induction machine. We have assumed that we have an electrical load which is pure resistive for this special case here. Then we have actual stator frequency. Actual stator frequency is not constant. The stator frequency here is not constant because the stator is not connected to the power grid. This is an isolated machine. Please keep in mind that a stator frequency is not constant. But anyway, we can draw a circuit which is referred to the actual stator frequency. All the elements here have a frequency equal to the actual stator frequency. We come and define two parameters. This is well known. One of them is known as per unit speed, which is B. B is per unit rotor speed, and A is per unit stator frequency. B is equal to omega m, mechanical speed divided by mechanical synchronous speed, or electrical rotor speed divided by electrical synchronous speed. and A is frequency of a stator divided by base electrical frequency. Base electrical frequency for us is, and you also is, 50 hertz. Then you have the definition, the old definition of slip was omega s minus omega m divided by omega s. If we replace from above, then we get that slip is A minus B divided by A. So for generating action, for generating mode of operation of this machine, we should have B is higher than A. It means that the per unit speed is higher than the per unit frequency of the machine. Here we had R2, of course R prime too, but the notations may differ from a reference to a reference. This is R2 divided by slip. R2 divided by slip is R2. A divided by A minus B. So this is here. The reactances are Jx is equal to JL 2P stator frequency, and a stator frequency is AFB, so it is JL 2P AFB, and so we have a reactance 2P FBL, and the actual reactance will be JAX, JAXN, JAX1, JAX2. X1 and X2 are the leakage reactances of the stator and rotor respectively. So the reactances here are functions of A. Then let's come to the capacitance. The capacitance is minus JXC divided by A. Why? Because the actual capacitance is minus J into 1 by 2P F stator C. Then replace Fs is A FB. Then it will be minus J XC base at base frequency divided by A. So we will have a division by A here. So this is a new equivalent circuit. You have not seen it in other machines. Here the reactances are multiplied by A, and the reactances of inductive reactances and the capacitive reactance, which is now 1 here, is divided by A. Please keep in mind that X1, X2, Xm, and Xc are evaluated at base frequency, not at actual frequency. So the problem here is that we are facing reactances which are not evaluated at the frequency of the circuit. The frequency of this circuit is F stator. But these reactants and other reactances are evaluated at F base. So in order to simplify, divide all the elements, all the impedances in the circuit by A, and also all the voltages are divided by A, then the currents will not alter because current is voltage divided by impedance. So we will have a new equivalent circuit in the next slide, in which the frequency is now constant, which is base frequency. The reactances are evaluated at constant base frequency, and the currents are the actual, but the voltages have been divided by A. So let's talk. This is current circuit that rated the stator frequency. You have divided by A. So R has changed to R divided by A. Minus JXC by A has been changed to minus JXC by A2. The voltage here is V1. V1 has been changed by V1 by A, and etc. R1 by R1 A. And so this is the frequency here. The frequency of this circuit is F base, which is constant. Then I explained that we would like to find the unknowns of this circuit. This is a case of the circuit, a version with RL load. If we have RL load, then R is divided by A at rated state of frequency, not at actual state of frequency. At actual state of frequency, we have constant R load, but here R load divided by A. And X, we had JA X load. In the actual circuit, X load is evaluated at constant frequency, which is base frequency. Then we divided the impedances by A, so this reactance is also divided by A, then we have J X load. So we are facing such circuits. And in these circuits, let's take a look at what are the known parameters and which are the unknown parameters which should be calculated. But before it, take several points in mind. The space harmonics of MMF and time harmonics of voltages and currents have been neglected. So in this circuit, we have just one frequency. We are not taking time harmonics of voltages and currents into account. Also, we have neglected core loss. In the proposed method, we can simply include the effect of core loss by a parallel resistance to JXM. Of course, that parallel resistance is not a constant. It is a function of voltage and frequency, but there's no problem in the proposed model to include such effects. And all the impedances are supposed to be constant except XM. Is there any question, Dr. Banerjee?
Sir, if we include the core branch, it would be RC by A. In this,
yes.
In this equivalent, it would be core resistance divided by A.
Yes, that's exactly. Yes, okay. Of course, this RC corresponds to the RC of the actual circuit.
Yes, sir.
Yes, I agree. Yes. Okay. I just wanted to let you know that different effects can be taken into account. Yes, exactly. And then this RC is a function. This RC is itself. This itself is function of frequency and voltage. Yes, sir. And this frequency is related to A. So we can say that we have a core resistance which depends on A and voltage. No problem. But yes, we should clearly show A division here in this equation. Okay, thank you.
Okay.
So let's go to the problem definition. I will try to go faster. We know all the equivalent circuit parameters except XM. We do not know XM. Why don't we know XM? Why don't we know the exact value of XM? What is the difference in this machine with other machines? In other machines, for example, in an induction motor, which is connected to the grid, then we suppose that we have XM, the value of XM. But here we don't know XM a priori. We should calculate it, and then we will have the value of XM. Why? Can anyone answer? The reason is that XM depends on saturation, and we don't know the operating point here. This is different to induction machine connected to the grid. An induction machine which is connected to the grid, then the stator voltage is fixed. Then we can assume that the voltage across XM is almost fixed, neglecting the drop across the stator leakage impedance. And also, if we have constant frequency, then we will have constant magnetizing current and constant value of LM, then constant value of XM. But here, due to saturation, LM, which is magnetizing inductance, is not constant. So when LM is not constant, then you don't know the value of XM. Of course, you know the frequency of this circuit. The frequency of this circuit is F base, no problem, because it is a rated state of frequency. but you don't know the value of inductance. So due to saturation, then you don't know Xn in the initial stage. We know R1, R2, X1, and X2. X1 and X2 are leakage reactances, so they are not affected by saturation, because the path of the saturation flux is almost totally in the air, not in the core. So leakage reactances are almost constant, but magnetizing reactance is not constant. In many machines that are connected to the grid, we approximate and assume that we have constant magnetizing reactance. For example, an induction motor, which is controlled by an inverter, we assume that we have constant Xm. Why? Because we are keeping in that case, we are keeping the ratio of voltage to frequency constant. So we have almost constant air gap flux. So we can assume that Xm is constant. But in this machine, we cannot assume that we have constant Xm. So we don't know the value. We will have to calculate. So we know all the parameters except X1, and also we know B. So B is known. We know B. B is the per unit speed. We know the rotational speed in per unit. We would like to calculate the A, which is the operating frequency. What will be the operating frequency? Of course, we know that A will be lower than B because the machine is in induction mode of operation. An induction machine of the squirrel cage type, of course, which operates in the generating region, the rotor speed, means B, should be higher than the synchronous speed that is related to A. We know B, but we would like to calculate A. And also, from the parameters, we would like to attain the value of the magnetizing reactance. Of course, after you calculate A and Xm, then you can go and calculate the voltages in the circuit. I will explain further. There are generally two methods, loop impedance method and nodal admittance method. I explained in the previous session. Let us take a review. For example, assume that we have a self-excited induction generator with RL load. We would like to calculate the unknowns, which are A here, and A here, and A here, and A here, 4 places. And also we would like to calculate Xm. We have 2 unknowns, A and Xm. This method, we use a KVL, ZS into IS. IS is here, IS. Of course, better to assume that its direction is here because the machine is generating, so it is feeding power here. So better to consider the direction of current from right to left from the rotor side, which the mechanical energy has been converted, the mechanical power has been converted to electrical, then come here, here, and here. Then, anyway, ZS into IS is 0 due to KVL. ZS is the total loop impedance, IS is not 0. Why? Because if IS is 0, then we have no power generated. So if the machine is really generating, then IS cannot be 0. How can ZS into IS be 0? Be 0 while IS is not 0, then ZS should be 0. ZS is equal to R1 divided by A plus JX1 plus the parallel combination of JXM and JX2 plus R2 plus divided by I minus B, and then we have also here. So this method is really involved because we have an equation with parallel branches which should be calculated by hand. Of course, this is apparently one equation. I just asked the previous session. This is one equation. We have 2 unknowns. How can it be possible to calculate 2 unknowns from just one equation? What was the answer? Can anyone respond?
Sir, you are told that they were real and imaginary part.
Yes, exactly. This is apparently one equation, but if we partition or separate it to two parts, the real and imaginary, then we will have two equations and we have two unknowns, so A and XM can be evaluated. The other method, the other well-known method is nodal admittance method. We can come across this node or this node and write KCL, Kirchhoff's current law. Then, for example, assume that we have come here. I will explain why this node is better than the left-hand side node. We have come here, then we have written KCL, YS is R1 by A plus JX1 plus this, and then it should be 1 divided by this, so the impedance and admittance, so Y is equal to Y1 Z, and then we have here the current here is E1 by Y, and also here E1 is not 0. Why? Because we have assumed that we have successful voltage buildup, then the addition or the summation of these three admittances across this node is known as air gap node. This is known as air gap node. The summation of the admittances across the air gap node should be 0. We could have used the same principle in this node also. Yes, this is known as capacitor node. But why do we prefer to use the nodal admittance method in this node, not in this node? Can anyone respond? This is an interesting question. Why do we prefer to use this method in the right-hand node? You don't see a reference using the nodal admittance method here to obtain A and X1. What's the reason? No ideas? If you take the real and imaginary parts of this equation, then in the real part, you will not have any effect from JXM. This is good because you don't know the value of JXM in the initial stage. But if you come here, you will have a real part and an imaginary part, and both are the JXM is taking part. Did you get my idea? If you come to the right-hand node, then in this node, JXM is taking part here in YM. If you take the real part of this equation, then the real part will be 0 from JXM. YM is pure imaginary. So the real part will just have one unknown, which is A. So if you take the real part of this equation, take the real part, then you will have one equation and one unknown. The unknown is A just. Dr. Banerjee, am I clear?
Yes, sir, totally.
Yes. So this is the reason that we use the node admittance method across the air gap node. We don't use the node admittance method across the capacitor. Of course, from the electrical circuit point of view, both the methods are equivalently correct, but it is much better to use this method just in the air gap node, because you can have one equation and one unknown, and this makes the problem much simpler. So analysis of equilibrium circuit, we have two unknowns, but apparently one equation, but one of the students replies that the comment was correct. That taking the real and imaginary parts of the equation, we have two unknowns and two equations just solvable, and we can obtain the voltage across XM or air gap voltage by the computed value of XM. How? I asked this the previous session, and the answer is that we can have a curve or a table giving the value of E in terms of XM. This is also related to saturation. And then using Xm, we can obtain the value of E. Of course, this E is at a fixed frequency, and then if you want to calculate the actual E, then you should multiply it by A. Why? Because all the components have been divided by A. So we have a circuit with constant frequency, but in the actual circuit, you will have to multiply each voltage of the circuit of base frequency by A to obtain the actual values of voltages. Of course, the currents do not differ. The currents of the two circuits are totally equal. Let's go to my proposed method. My proposed method is based on the nodal admittance method. I come to this node, and then I take the real part of the admittance. As I mentioned before, if you take the real part of the admittance, then you will not have any contribution by this. This will not have any contribution to the real part of the admittance at the air gap node. So you will have an admittance, a real part of admittance. What is the real part of admittance known as? What is the name of the real of admittance from the equivalent circuits, from the electrical circuits? What is the real of admittance? It is known as what?
Conductance, sir.
Yes, the conductance. So let's equate the conductance of the air gap node. Let's equate the conductance of the air gap node to 0. What can affect the value of the conductance of the air gap node? Just A. Do you agree? Because all the other parameters are constant and known. Jxm does not play any role in the conductance across the air gap. So we will just have to change A and see whether the value of the conductance is 0 or not. That is my proposal for finding the value of A. So in my method, I first find A using the conductance method, the conductance across the air gap branch. Then if I found A, then I can come and also obtain the value of Xm. I will explain it. So if I want to explain more, I should say that you change the per unit state of frequency A in steps from below per unit speed B to a value close to it. For instance, close to it is 0.99 B. It is really close to B. For example, from 0.7 to 0.99 of B, 0.7 B to 0.99 of B, you change it. A is equal to this. And then for any value of A, you calculate the real part of the admittance, that is conductance across the area. Then there should be a value of A which makes the value of the conductance equal to 0. Of course, in computer simulations, maybe the value of the conductance is not exactly equal to 0. So you can find the minimum value of the conductance. The minimum value of conductance should be a value exactly equal to 0, really close to 0. That will be the operating unit frequency A. You save the value of the conductance in an array, and the value of A yielding minimum conductance is the solution for the per unit frequency, that is A. So after you find A, you equate the imaginary part of the admittance across area voltage. At this stage, you have A, and you just don't know the value of Xn. So when you equate the imaginary part of the admittance, by the way, it is known as susceptance. You equate it to 0, then you will find the value of operating magnetizing reactance. This is really simple because you know A, you know the susceptance of all the branches, you know the values of all the branches, and you just want to calculate Xn. When you equate susceptance to 0, then you can find by a simple equation, does not need any iterative method, you will find the value of Xn. After finding Xn, you can calculate the air gap voltage using the saturation characteristics, and after you obtain the value of the air gap voltage, E1 in my figure, then you can calculate the rest of voltage and current. This is really simple because you have a circuit, you know a voltage in one part, and you can calculate the currents and voltages in the rest of the circuit. We should take care and caution that calculated currents are acceptable, are the actual currents, but the voltages that you have calculated above are for the base frequency. If you want to know the actual voltages, you should multiply each voltage by 8 to obtain the actual value, because the circuit that we were using was at a base frequency, and all the voltages had been divided by A. So you should go back to the actual frequency. You should multiply voltages by A. This is clear. And these are simple circuit equations. You come here and R load by A plus JX load here. This is the impedance. Then you parallel these two impedances, that is ZC, and then you add ZC by this impedance, and then you divide this impedance, you divide 1 by this impedance, and then you come here to the rotor side, you calculate Z of rotor, 1 by Z of rotor is Y rotor, and then you have G is the conductance, G is real part of Y stator, real part of admittance is known as conductance, and also here, then G stator plus G rotor should be 0, but you find a value of A which minimizes absolute of G stator plus G rotor, and then that A will be the working frequency. I have here one question. Maybe in some cases, for a particular rotational speed and particular value of capacitance, actually you will not have successful voltage buildup. My question is that how can we observe it in our calculations? How can we observe if that operating point is feasible or not? I mean that how can we observe that for a specific value of capacitance and rotational speed, then we can generate voltage or not? Of course, I have written a hint here. That is by inspecting the calculated magnetizing inductance value. But can anyone magnetizing? Let me explain reactance, because we have magnetizing reactance calculated. How? This is a hint. Please explain. We calculate Xm. Then if Xm is negative, then the point is not feasible. Xm is higher than Xm max, then the point is also not feasible. Xm should be between these two values, Xm between 0 and Xm max. Xm max is unsaturated value. Unsaturated value. So you know that if you have saturation, then the reluctance increases and the magnetizing inductance and the magnetic reactance decrease. So you will have this constraint. This is the constraint. After you calculate Xm, you should check if Xm satisfies this inequality, then that operating point is feasible. But in case Xm is negative or higher than this unsaturated value, reactance cannot be higher than the unsaturated value. So in this case, in these cases, you don't have actually successful voltage buildup. An interesting characteristic of my method is that it can be generalized. For example, generalize to RC loads or to cases that we have a series capacitance for compensating reactive power. This compensation you have seen before in DC machines. You have compound machines, series and shunt compensation. In the compound machine, you have a series winding and a shunt winding. The series field is advantageous because the field is in proportion to the current. So when you take more current, the voltage is going to decrease generally, but when you pass more current through this series capacitance, then it will provide more reactive power. Then providing more reactive power will aid and help the voltage. So you will have better regulation. In my method, it makes no difference. You come here, or in this circuit, you come here, and then you equate the value of the conductance across the magnetizing or the air gap branch to 0, and then you will find the A that minimizes the value of the conductance. After you find A, then you can find Xn. Just the circuit equations are different, but you don't want to manipulate these equations by hand. This is in contrast to the previous methods, which you should calculate the real and the imaginary parts by hand and derive that equation. But here you don't want to derive the equation by hand. You just write the values of the branches in your code. Another part of my webinar is dedicated to calculating the minimum required capacitance. You know that capacitance should be present there at the terminals because we don't have a source of reactive power in the machine, so we should provide it locally. The machine is RL, the load is generally RL, so we should have capacitors across the stator terminals of SEIG. The value of capacitance should be more than a specific value. It should be higher than one value. If it is very low, if the capacitance is very low, then it cannot aid the voltage which is built by residual and improve and increase that voltage to the rated value. So a very small capacitance value is not acceptable here. The capacitance should be higher than a specified value. In this part of my presentation, I would like to tell you how we can calculate the minimum required capacitance. In order to calculate minimum capacitance, we should set Xm is equal to Xm max, which is the unsaturated magnetizing reactance. Why? Because as I mentioned before, here you have two curves. As you increase the capacitance, then you decrease Xc, so you are going further here. The minimum capacitance means you are decreasing the capacitance, then you come here, then you are at the unsaturated region. So C mean is in correspondence to Xm maximum value. So this is a hint to obtain the value of the minimum capacitance. By the way, this is interesting point. In most of the papers that you are calculating the minimum capacitance, they have neglected the value of core loss. What's the reason? In the papers calculating the capacitance requirements, this is not the capacitor requirements of the seig, they neglect core loss. What is the reason? Do we have my sound, Dr. Banerjee?
Yes, sir. You are totally audible.
Yes. What's the reason? The reason is written above. Because C mean corresponds to Xm max. Xm max corresponds to unsaturated region of the magnetic path of the machine. If the magnetic path of the machine is unsaturated, then you can neglect core loss. So when you want to calculate the capacitance requirements, you can neglect core loss. So you don't include resistance RC divided by A in that equivalency. But if you want to calculate the performance, if you know the capacitance and you want to obtain the performance of the machine, then you can include core loss that will yield more accurate results. But in this stage, when you want to calculate the capacitance requirements, it is not common to include the core loss resistance. Then, what are the advantages and disadvantages of a capacitance, the higher value or low value? Disadvantages of the higher capacitance is that a high capacitance, the more the capacitance, the high value of capacitance leads to more copper losses of stator rotor and less efficiency. The more the capacitance, the more the terminal voltage which can deteriorate the insulations. And the more the capacitance, the less the frequency. Of course, you should check this. You should check this. And also you should check this. And also the currents by simulations. But these are the final derivations. The final conclusion is that if you increase the capacitance, then you have increased the currents and also the terminal voltage, and also you have decreased the frequency. On the other hand, the advantages of a high value of capacitance is that if you have a higher capacitance, then you have more current capability of the generator. You can deliver more current by the generator, and you have less voltage regulation. The voltage regulation will be a smaller value. Of course, these should be checked by simulations. In an actual practice, there should be compromise between the above issues to select the value of the capacitance. Here, we don't want to discuss the compromises. We just want to discuss the minimum value of the capacitance. To calculate the minimum value of the required capacitance, you look through the capacitance branch. I mean this. You come here, then you equate Y, this is admittance across this branch, into the voltage. Voltage here is V divided by A. This will be 0. Again, what should be 0? Voltage is not 0 because you have assumed that you have successful voltage buildup. So VT divided by A is not 0. Then YC is 0. When YC is 0, then the conductance will be 0. And also the susceptance will be 0. Then here XM is known or unknown. It is known. Why? Because you want to calculate C mean. So Xn is equal to Xn unsat, or maximum value. You want to calculate the capacitance. Then this further. You again vary the per unit frequency between a fraction of B and a value close to B. Calculate conductance. If you calculate the conductance, you know that in the conductance, you don't have any effect by the value of XC. So you first obtain the value of A under such circumstances. This is interesting. You want to calculate the minimum capacitance, but first you set Xm equal to Xm unsat, which is a fixed value. You fix Xm, X will be constant. Then you find A. You find A in this circuit. What value of A leads to minimum conductance value? So you find A, and after you find A, then you come equate the imaginary part of the admittance, that is the susceptance to 0. Then you find XC, which is XC. That is the way. You don't find firstly the minimum value of C. You first find A. When you are finding A, you know B. B is known, because when someone asks you the required capacitance, then you should know the rotational speed of the rotor. If you change the rotational speed, then there will be another value of XC mean. You have a constant B, you have constant other parameters. Then Xm also is constant here. Why is constant? Because you know that if Xc is going to be the minimum value, then the corresponding value of magnetizing reactance should be unsaturated value, which is the maximum value, which is known from the curves. You can obtain Xm value, unsaturated Xm value by experiment, by using the saturation characteristic of the machine. Then you change A. After you change A, you obtain the correct value of A. The correct value of A is that value of A which GC is 0. GC is 0, you obtain A. After you obtain A, then you go to the imaginary part of the admittance. You equate BC to 0. And after that, you can find XC of minimum. So using the minimum common in MATLAB, one can find the corresponding A. So firstly, A is found, then XC can now be determined equating BC to 0. BC is this. This is the conductance. BC is the conductance. Of course, as I mentioned, yes, here, you can analyze a seig with core loss. Here, Dr. Banji, do you see this? Here, RC is divided by A.
Yes,
the proposed
sir,
method can, yes, the proposed method can be generalized. To analyze SEIGs with core loss. We should just modify the expression for YC, and also in case we want to calculate the performance, we should come here and equate the real and imaginary parts of the admittance to 0, and you can analyze the circuit. So this method is general. I have here shown you several simulation results. For example, I have shown that if you change the load resistance, if you increase the load resistance, how the generated frequency per unit changes. Please keep in mind that the generated frequency is below 1 because I have assumed that B is equal to 1 per unit. So per unit frequency, which is A, this is A is less than 1 because B is equal to 1. I have simulated 3 methods. One of them is my own method. This is suggested method. The others are 2 methods by Dr. Macpherson from his book, Electric Machines and Transformers by Professor Macpherson. And also he has a paper on self-exact induction. Then other method is an iterative method by Dr. Chang. So I have simulated, and you see that the methods give similar results, but if you take the details, then my method is really simpler because it can be generalized to other cases with RC load, with series compensation, or with core loss resistance. Here you see that as you increase the load resistance, you see that the magnetizing inductance changes dramatically. You cannot assume that the magnetizing reactance is a constant value. As you increase the load resistance, then the magnetizing reactance will be lower. That is, as you decrease the current drawn, then you will have lower magnetizing reactance. Lower magnetizing reactance means higher reluctance. You should analyze each figure in detail. Let me go to the other piece. This is the relation between speed and frequency. In this simulation, I have assumed that I am changing B. This is speed is B. I have changed B and I have observed A. At any point, B is a bit higher than A because we are in generating mode, and there is almost a linear
अरे रिकॉर्डिंग ऑफ मत करो, वो शायद लॉग आउट हो गए हैं. रुको रुको. वरुण 10-15 मिनट और चलेगा बस, ठीक है. शायद उन लोगों की तरफ कुछ पावर आउटेज वगैरह हुआ है, पूछता हूं मैं. Engineer Karamati. Engineer Karamati, are you able to hear me?
Yes, Dr. Banerjee. I don't know what happened.
Yeah, because sir has most probably logged out. I'm just
Let
trying
me
to
call
contact. Yes, yes, yes. Please call him once.
Let me call.
Sure,
Let
sure.
me
sure.
call him.
I'm coming in. It seems that you have scheduled it to be just 1 hour, and that's the problem.
Sir, it's scheduled to be till 3:45. That means we have still 15 minutes, sir.
No, it seems that you had scheduled it for just 1 hour. Then it logged me out.
There must be some other problem, sir, because I can show you the schedule. It is from 3:15 to, 2:15 to 3:45 for 1.5 hours.
So, what's the problem?
Might be some kind of connectivity issue, sir.
Okay. Oh,
You
everyone
can,
is leaving. Every student is leaving here.
sir, some of the students thought that maybe the presentation is over, so probably some of them left because of that.
No.
You can continue, sir. We have still some more time.
I don't see any screen of attendees in
Sir, you
the
will have to
webinar.
project it again.
It's not possible. No.
Dr. Banerjee, excuse me.
Yes, Engineer Karamati.
Dr. Banerjee, you said the meeting time for 1 hour or something like that?
1 hour 30 minutes. I mean, it's from 2:15 Indian time to 3:45 Indian time. That would probably translate to 12:15 Iranian time to
Yes, yes.
1:45 Iranian time.
45.
Yeah. Is it not possible right now to project the screen again, sir? Nasir, sir?
Dr. Hashemnia? No, something is wrong.
This might be some kind of connectivity issue. Otherwise, there won't be any problem in logging things in.
It seems something is wrong because all Iranian students was log out.
I'll just check it. I'll resend the link again to you all. I'll just resend it. Might be some kind of connectivity issue.
Let me see.
Nasir sir has sent a message. Let me check.
Well, something is wrong. It seems that no. Yes, all Iranian students. No. Someone are present.
Okay, the participants are requested to stay put. I'm just interacting with sir. Probably there is some kind of connectivity issue. Nasir sir, I have mailed the link again. Please check if you are able to log in. मैं उस पे बोल रहा था सर से. I mean, I was talking over WhatsApp. My mic here remained on. Yes, sir has logged in again.
Yes, it seemed that there was a problem with by Google Meet.
Yes, sir. Might be some kind of a software or connectivity issue. In Google Meet, sir, it doesn't automatically log out the participants. Once the time duration is over, a person can continue.
Okay, I didn't know. Okay, so from what slide should I continue?
You were showing us the results of speed versus frequency, I presume.
Okay, so you have not missed much of it.
No.
Yes. So, okay, this shows. Do you have my screen?
Yes, sir. It is visible.
Okay. Oh, thank you. So you have here. This is the variation of the generated frequency when you change the rotational speed of the rotor of the self-excited induction generator. As expected, the more the speed, the more the frequency. But of course, this is an asynchronous machine. So A, which is this axis, is less than B, which is this axis. It means that, for example, if the speed is 1 per unit, then the generator frequency might be 0.90, 0.9 or 0.91, 0.92 per unit. A is close to B, of course, but it is less than it. Then I explained this. This is the loading characteristic of the generator, or the output characteristic. The output characteristic is the volt ampere characteristic. How have I obtained this characteristic? I have changed the value of the resistance of the load. I've assumed that my load is pure resistive. Of course, the similar can be again simulated for RL and RC loads. And I changed the value of the load, and I observed the load current and the terminal voltage. This is an issue known as voltage instability. The stable portion is this portion, the above portion is stable, and this portion is the unstable region. So the stable portion is that portion when you increase load current, then naturally the terminal voltage will reduce. This characteristic is also observed in self-excited DC machines. See, in self-excited DC machines also you have such characteristic. And also, as I mentioned, you have automatic protection. You see, as I am decreasing the resistance of the load or an increase in load current, then I have load current increasing, voltage reducing. If I go further, then I will go to a high value of current, but the value of current will not be, in this case, higher than 0.6 per unit. You see, the automatic protection is also observed here. And finally, this is simulation of the capacitance requirement with load resistance using 3 methods. The 3 methods, one of them is mine and two of by Dr. Harrington, who is an active person on capacitance requirements. And these are his papers, New Insights for Capacitance Requirements for Isolated Induction Generators, and New Approach to Determine the Critical Capacitance for Self-Excited Induction Generators. And here I draw the conclusion, and a simple and innovative method to analyze the steady-state performance of a self-excited induction generator with core loss. Core loss can also be included, but present among the priorities of this method over the more common methods. The common methods are simply load impedance and node admittance methods. The priorities of this method are the ability to be simply augmented. It can be augmented to different cases. For example, different loads and absence of also convergence problem. And this approach can be used in windmills to predict the steady state performance of the system. Thank you very much. I hope my webinar has been useful to you, and I'm eager to answer the questions and also collaborate with Dr. Banerjee and his students to make several experiments and also simulations on self-excited induction generators. Thank you very much. Please ask any queries.
Thank you so much, sir. It was a wonderfully given webinar in which you gave us deep insight into the operation of separately excited induction generators. So I have one question, sir, and apart from that, my students, the student group which would be dealing with SEIG would also be interacting with you for probably a couple of minutes. Prior to that, if
Yes.
any student has any question, he or she may please ask.
Yes.
If any student from India or Iran has any sort of question, he or she may ask, sir, right away. After that, we would commence our research discussion. Okay, so no questions from the students. So, sir, I just had one query. Constructionally, is there any difference between the fabrication of an induction generator and an induction motor? Usually in India, the synchronous machines are mostly synchronous generators, and the induction machines are mostly induction motors. So if someone constructs an induction generator, which is supposed to be used as a generator only, would its make or construction be different from that of a usual induction motor?
Actually, the mostly today, up to now, most of the induction generators which have been used are the grid connected ones, and they are wound rotor induction generators with variable rotor resistance, which is known as VRCC. This is by Vestas, the technology by Vestas. Also doubly fed induction generators, which are different from this one. This machine has the advantage of simplicity, and the advantage that you can use an induction motor, which you have already available, an induction generator. You see, the machine is just that induction motor, but you are using it as an induction generator, and you don't want to have any power electronic interfaces. See, you just need capacitance. The capacitors also can be switching capacitors, or they can be fixed capacitors. But to answer your question, the construction of the machine is similar. You have a squirrel cage rotor, and the machine is available. You have many induction motors available, squirrel cage induction motors. Then you can use as induction generators. Of course, I know maybe you mean that the optimized induction generator can be different from optimized induction motors, but this is out of my scope. My scope is not electric machine design. I assume that we have an induction motor in hand, then we want to use it as an induction generator. If we have the parameters of that induction motor, then we can calculate the capacitance value, which leads to generating mode of operation.
Okay, sir. Thank you so much, sir. Okay, so
Of course,
yes, sir.
I am not involved with machine design. If you machine designs, there is difference between motor and generator. Yes,
Okay, sir.
that's correct. Yes.
Thank you, sir. Thank you so much. Okay, so apart from my group, my research group, other students may please leave. Apart from my research group, the SCIG research group, other students may leave. Ha, Varun. You can stop the recording and leave. So, Varun, you just send the link to me so that I can forward it to Dr. Hashim Nia. Okay, welcome.
Yes,
Okay.
Mr. Verma, Mr. Varun Verma, do you have any questions?
Sir, he was recording the meeting, sir. So he would be sending the link.
Thank you.
He was seeking permission to just log out now because the recording is complete. Okay, so
Yes.
Henna, Saurabh, Vansh, and Piyush, you four are here.